Hi. So today's topic is cell, EMF and internal resistance. So the device which provides steady current in an electric circuit is called electrical cell. Simply, the basic construction of a cell, I am going to draw a cell. It consists of two metallic rods that are called electrodes. They may be one may be copper rod, another may be zinc rod, and it is dipped in any liquid which is called electrolyte. Now, these transfer charges, these electrodes and electrolyte, they transfer charges. So, let me first of all write all the points. These are the basic devices that provide steady current. In an electric circuit. Now, steady current can be provided by so many other devices. We know generator. So, in generator, the EMF is provided by, the source of EMF is mechanical energy. But in your cells, source of EMF is chemical energy. Here, the source of EMF is chemical energy stored in electrolyte. So, in these devices, there is transfer of charges from electrode to electrolyte. There is transfer of between electrodes and electrolyte. So next point is, these electrodes, when they are dipped in this electrolyte, they have different their electronegativity. The electrodes have their different reactivity with electrodes and electrolyte. Okay, these electrodes have different reactivity with electrolyte. They have different electronegativity. So they develop different potentials with respect to this electrolyte. They develop because they are different materials. Zinc is more electronegative than copper, and zinc will react differently with electrolyte. Copper will react differently with electrolyte, and they develop different potentials. With respect to electrolyte. Okay, so let me draw once again here at this point. So we have an electrolyte, and in which two rods are submerged. Suppose this is your positive electrode and this one is your negative electrode. Okay, so it develops some potential, let it is plus V potential. This point P develops plus V potential with respect to a point in electrolyte which is close to this electrode. Suppose this point is A. And this negative electrode develops some negative potential minus V with respect to a point near to this electrode in electrolyte. Okay. So you can see that it is at negative potential. So when at a point Q, so what will be potential from B to Q? Means VB minus VQ. So since it is Q is at a negative potential and B will be obviously at a greater potential. So higher minus this minus. It is at a V minus. Okay, so you can this will become, because it is negative, minus of this minus V minus. So it will become your plus V minus. Okay. It will be a positive value because you are going from a higher potential to a lower potential because it is at a negative value. So let me write potential difference between point P and point Q. Now potential difference between point P and Q, VPQ can be written as VP minus VA, potential between these 2 points, now plus VA minus VB, potential difference between the 2 points in the electrolyte itself, between point A and point B, and finally plus potential difference between point B and point Q. Okay, so we have to write down 3 potential differences. Now VA is equal to VB as there is no current flowing in open circuit. Therefore VPQ comes equal to, this is your V plus, here I have written V plus, positive, it is positive. And this potential difference, VA minus VB, it is your 0 because no current is flowing. And if let and an internal resistance of electrolyte, okay, let me delete this thing first of all. Internal resistance of electrolyte as the electrolyte is opposing the, so there is some internal resistance of electrolyte and which oppose the flow of charges through the electrolyte. Okay, and let that resistance is equal to R. Now in equation 1, here we have it in equation 1, VPQ is equal to, this potential difference I have already taken, this is your V plus, okay, V plus, since no current is flowing, had the current flowing, I current flowing, then potential difference, this potential difference would be I into this internal resistance R. But since the current is not flowing, so IR, here I is equal to 0, so potential difference becomes equal to 0, and then VV minus VQ, this potential, this is your plus V minus. So it comes equal to V plus plus V minus, and this is equal to, if we take E, that is called EMF, electromotive force. Let me delete this. Electromotive force. The name misleads you towards some force, but this due to some error that is made in history, so it is named as force, but it is work done. What is electromotive force? Electromotive force is work done, because here you have potential, so potential used to be work done. So electromotive force is work done. Now this work done is not of electric nature, though it is numerically equal to potential difference, but it is not of electric nature. It is work done by chemical source, work done by some chemical nature, work done of some chemical nature, in bringing unit charge from one electrode to another electrode, from negative electrode to positive electrode. Negative from one electrode, let me say, from one electrode to another electrode. Why I have deleted negative charges? Because in electrolyte both kind of ions flow, positive ions as well as negative ions. So you should mention that it is flow of it is work done in bringing unit charge from one electrode to another electrode. Okay. So in a cell, this is in a cell. In a generator you have this electromotive force of mechanical nature. In generator, this EMF is of a mechanical nature. Means this work done is of mechanical nature. Let me write here work done. Okay, so what is EMF? EMF is work done in bringing unit positive charge from one electrode to another electrode in an open circuit. Okay, so this is your in an open circuit when you have not connected it through outer any resistance. In an open circuit, this is in an open circuit. So this is your equation 2. This is your equation 2. So this potential difference, if you consider it as V comes equal to EMF in open circuit, VPQ, okay, VPQ is equal to EMF. Now let us connect in the external circuit a resistance R. In this way, I am connecting a resistor R in external circuit so that I current starts flowing. As the circuit is complete, we have closed continuous path, so we can assume that a current starts flowing. Okay. As we have closed continuous path, a I current starts flowing. Now in equation 1, so we have potential difference VPQ is equal to this term, as before, this term potential difference between point P and point A is same V plus, so it is your V plus. Okay. And plus this term VAB. Now a current is flowing in outer circuit, it is from P to Q, but in inner circuit it is from B to A. In outer circuit it is from A to B. combination of these cells. There are two ways by which we can combine the cells. So first way is series combination. In this kind of combination, the cells are connected end to end, side by side. Suppose we have two terminals of this cell which is having EMF E1, and this is second cell which is having EMF E2, and its terminals A and C. Here C is common terminal of E1 and E2, and here we have another terminal B. Now now we have the same current is flowing. If a potential difference between point A and C is V1, and potential difference between the point C and B is V2, and since in series combination we know that same current flows through the circuit, so here current is same, current I is same. Now net potential across AB is V net, then V can be written as V1 plus V2. V is the net potential difference across AC plus potential difference across CB. And we know that since V1 is equal to E1 minus IR1 and V2 is equal to E2 minus IR2, where R1 and R2 are the internal resistances. Or cells of the cells. Now let me put the value of V1 and V2 in this equation. Therefore V is equal to E1 minus IR1 plus E2 minus IR2, and this is equal to E1 plus E2 minus I into R1 plus R2. Now if we replace the combination of these two cells by a single cell which is providing the same current I, then we can replace this way. Now if the combination with a single cell with EMF E and current I is same current I, is flowing, then V is equal to E minus flowing across the same across the internal resistance R, then V is equal to E minus IR. So from 1 and 2, let me delete this, from this 1 and this 2, E minus IR comes equal to E1 plus E2 minus I into R1 plus R2. So when you equate the two sides, on equating the two sides, net EMF equivalent can be equal to E1 plus E2, and resistance equivalent, okay, internal equivalent is equal to R equivalent is equal to R1 plus R2, and this is justified also as the cells are connected in series, so resistances are connected in series, and we got equivalent resistance which is equal to R1 plus R2. Now suppose we have N cells. With EMFs E1, E2, E3 up to En, and internal resistances R1, R2, R3 up to Rn, then your E equivalent, EMF equivalent is equal to E1 plus E2 plus up to En, and R equivalent is equal to R1 plus R2 plus up to Rn. Now one more condition, when in this equation, here we have the two cells connected in opposite senses in equation, okay, in this equation, in equation A. When in equation A, the two cells are connected in opposite sense. In this way, look, the two positive terminals are alongside. Suppose it is E1, it is having EMF E2, then in equation A, we will take E2 with a negative sign. We will take one cell with EMF with negative sign, and here you have minus I into, and resistances will be same because it does not change with polarity. Your equivalent resistance will remain same. This is equal to E minus IR. So now EMF comes equal to E1 minus E2. The cell which is with opposite polarity is written with a negative sign, and rest thing are same, means R equivalent is same, R1 plus R2. So now next combination, parallel combination of cells. parallel combination of cells. Okay. So if the given two cells are connected on the same common terminal, you know parallel combination? Two resistors or any two electric device, when they are connected on the same common terminal, then such combination is called parallel combination. So I will not exaggerate very much. In simple way I am going to simplify the equation. Here suppose I current is flowing externally in between point A and B, and here you have I1 current and here you have I2 current, and it has potential difference same. Suppose potential difference is V for battery with cell with EMF E1. So potential difference will remain V for cell with EMF E2. Suppose it has internal resistance R1, it has internal resistance R2. So now let me write equation directly. I am not going to explain every terms. So you will be doing this. Here V is same, so we will not take V, we will take I. I is equal to I1 plus I2. This is one equation. Now we know that V is equal to E minus IR. Therefore, I is equal to V minus, okay, let me delete. I is equal to E minus V upon R. So we will be putting value of every I as per this equation in equation 1. So in equation 1, I can be written as, in place of I1 will be, because it is I equivalent, so I am not writing the value of I equivalent, I am putting the value of I1. It is equal to E1 minus V upon R1 plus E2 minus V upon R2. So you get that E1 by R1 plus E2 upon R2 minus V into 1 by, okay, let me delete this. This is your V. V into 1 by R1 plus 1 by R2. So if you replace the combination with one single cell, when the combination is replaced with one single cell of EMF E, which produces the same current I, which produces the same potential difference V. Because here in parallel combination we have current not same, we have potential difference same across the cells. So if we replace the combination of these cells with a single cell of EMF E and internal resistance R, which produces the same PdV and having internal resistance R, then I equivalent should be equal to E minus Okay, V is equal to, this is equal, V is equal to E I equivalent into R. This was your, let me simplify this. Therefore, I equivalent comes equal to E minus V upon R. R equivalent, okay. So let me simplify this. Therefore, V into R1, R2, R1 plus R2. I have just simplified this and I brought this part along this side of equation, and I am taking I equivalent on the other side. So it becomes equal to E1 R2 plus E2 R1 upon R1 R2, okay, minus I equivalent. Therefore, V comes equal to E1 R2 plus E2 R1 upon okay, let me divide this term on this side. So when you will be dividing this term, you will find that this is equal to R1 R2 into R1 R2 divided by R1 plus R2 minus I equivalent into R1 R2 divided by R1 plus R2. So let me cancel, and V is equal to E1 R2 plus E2 R1 upon R1 plus R2 minus I equivalent into 1 by R1 R2 divided by R1 plus R2. This is your okay. So this implies that E equivalent, okay, when you compare this with okay, now let there be a cell which is producing cell with EMF, okay, cell EMF E, which is producing the same current I equivalent, and its internal resistance is R equivalent and potential difference across the cell is V. PD across the cell is V. Then let me name this equation A. Then V is equal to E minus I equivalent into R equivalent. So when you compare A and B, on comparing A and B, we find that E equivalent or E minus I equivalent R equivalent is equal to let me write here equivalent only, is equal to E1 R2 plus E2 R1 upon R1 plus R2 minus I equivalent into R1 R2 upon R1 plus R2. It implies that E equivalent in parallel is equal to E1 R2 plus E2 R1 upon R1 plus R2, and R equivalent is equal to R1 R2 upon R1 plus R2. It implies that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. So it is justified. We know from before that in parallel combination of two resistors, the resistors are combined in this way. Now suppose we have by this equation, this is very important equation, suppose we have N cells, so the equation can be obtained using this. Let me write it as C, equation C. Now, if we have N cells with EMF E1, E2 up to En and internal resistances R1, R2 up to Rn, then from equation 3, equation C, okay, this was equation C, we get that I equivalent is equal to, from here you can see, E1 by R1, E1 by R1 plus E2 upon R2 plus up to En upon Rn, and minus, here you have minus, V into 1 upon R1 plus 1 upon R2 plus up to 1 upon Rn. So this is how you will be connecting more cells by this equation. This equation is very vital, very important. If you have more than 2 cells, you have 3 cells, you have 4 cells, you can use this equation. This equation is not as useful while connecting more than 2 cells. So for connecting more than 2 cells, you will be using this equation. Now suppose if out of 2 cells, one cell is oppositely connected. The polarity is just opposite. If the polarity of one cell is opposite, in this way, suppose one has positive terminal along this side, other has positive terminal along another side. So in this case you will be writing by changing the sign of this E2 in this way. E1 upon R1 minus E2 upon R2 minus V into 1 upon, okay, the resistors, it does not change with the change of polarity, so it will remain same. And E equivalent can be written as E1 R2 minus E2 R1 upon R1 plus R2. So this way you will be doing the combination of the cells. There are so many questions, so we will discuss in next class.